Thank you, Hugo. Welcome, everyone. I want to talk today about the model-based sensor fusion approach for force and shape estimation in soft robots. So my background during my PhD is on sensing, on tactile and proximity sensing, capacitive sensing. And since my postdoc here, I've been looking into how to integrate these sensing ideas to deformable devices. And what's interesting of this domain in general is that soft robotics has brought about many new ideas on how to implement sensing, because the traditional sensing paradigms are challenged. But however, many of the approaches for modeling are based on data-driven. So we're using some kind of regressions or machine learning models that have to be trained in advance, but don't necessarily use a physical model behind to explain the measurements. And SOFA offers the opportunity to use a physics-based model to support sensing, and this is what I've been investigating. In this presentation, on this work, we had two devices. We have a soft pad that could be thought of as a tactile sensor, a touch pad, and also a finger. So you see on the left the touch pad and its deformation, as well as a soft finger, which we can use in a gripper. And the main takeaway from this work is that the numerical model, the FEM, mediates the sensor fusion. So to talk about how the devices are conceived, so that they are deformable, and we try to make them of a uniform material, so it's a slab of silicon. And for tactile sensing, I continue on the idea of capacitive sensing, and we use a deformable capacitive array using a liquid metal alloy for the electrodes. So this is a really highly stretchable, highly deformable pad realized here in this special technique of fabrication. And using a self-capacitive sensing principle, which measures the coupling of each of these electrodes with the environment, we can reconstruct a capacitive image. So we have an arrangement of rows and an arrangement, and an arrangement of columns. And by sensing and time multiplexing, we can reconstruct the location of the touch interaction. For sensing of the deformation, we have cavities embedded in the structure, which are shown here as 4 of them, which will help us then estimate the changes in force. So basically, as we push on the device, air will be pushed out of these cavities, and we measure this change in volume. For the finger, we have basically the same arrangement. We have overall deformable structure, this time also including a cable. We have embedded some electrodes. This time it was a copper foil, but I think we can show the same results as for the deformable for the liquid metal electrodes. Again, in self-capacitive sensing, we're trying to find the contact location. And on the right, we see the arrangement of the cavities inside, which allow us to sense the volume changes as well. So we can have an estimate of the deformation. And I just want to briefly talk about how we use the modeling capabilities in SOFA to include these sensing streams. So first, we have this constraint-based modeling approach. So we have, on the one hand, we have the global forces and internal elastic forces that are being solved in the quasi-static regime, and we have external constraints or constraining forces that we can define. So for instance, we can have a force variable lambda, which applies a uniform or weighted pressure on some nodes in our FEM mesh. This is one way we can use it. So this one will simulate the pushing that we will need for both the finger and the pad. But the same type of idea can be applied, for instance, to cable actuation, and this is related to Eunice's talk, because this is a more simple model than what Eunice was talking about. This doesn't really simulate the physics of the cable, but it allows to simulate approximately how the forces of the cable are applied to the model. So I won't go into the detail, but it's just to say that you have, again, a force variable that allows to apply forces to the model and have a bending resulting from the force or the displacement on the cable. Okay, and at this point I would like to share a YouTube video. Oh, let's go back. Where am I? Wait. Okay.
It seems the video is unavailable. Can you see the same or?
Yeah. Watch this. Okay. Maybe I have to share my screen, right?
Yeah. So, go ahead. It's the fourth button on the right middle in the interface.
I hope you can see the video.
So it's loading. Perfect. Yeah.
Okay. So this is the video is to illustrate again these ideas. So just to quickly say that we have on the one hand the capacitive image showing the location of the contact interaction, and we have the changes in volume, and then we have our device here. And it's important to say that the detection of the contact is also robust to the deformation. So the capacitive touch pad being stretchable, being deformable, first it's not breaking, but also it's somewhat insensitive to the deformation happening, and so it continues to give a good output of the contact location. And here you see a little bit the red area indicating the selection of the nodes on which we want to apply our force constraint, as well as here seeing the deformation happening in our cavity model. And for the finger, I think this is I'm really happy about the results here, because we can really see that we have a very flexible interaction with the finger, having many possible contact interaction points, and having also a quite nice reconstruction of the shape of the finger. And also we have the possibility of multiple interaction points. So the multi-touch availability is not restricted by SOFA, but by the sensing principle. So previously on the touchpad, it was more difficult to implement multi-touch, but from the modeling perspective, it's not a problem at all. It's not increasing the complexity very much. And here we see also the interaction when we have some forces being applied to the cable. So we can include many different causes for that explain the deformation. All right. Okay, so I guess to round off this talk, I just want to briefly talk again about the modeling behind it. So this is all based around the fact that using the FAM, we can define these external forces which will induce a motion on the nodes. And we have our cavity model, which uses a surface mesh from which we calculate the cavity volume, and there's a mapping between the change in force to the change in volume of the cavities. And so in SOFA, we have our external force variable, which is mapped to the node movement, which in turn, using this function of phi, which represents the volume function of the cavity. And here we have its derivative with respect to the node motion. So we can find the direct relationship between the force variable and the change of the simulated volume. And what we do is to minimize the difference between the simulated volume. So we'll find the value of the force variable that will minimize the difference between the simulated volume and the real measured volume. And this is what allows us to reconstruct the shapes and forces. So after this, we have some of the evaluation, which you will find in the the paper. But I think so. The main idea is really to show that this concept works, and I think there's a lot of room for continuing this work, improving the accuracy, but also extending the use cases. For instance, to design what could be called anatomical soft robots, which are phantoms for medical training that can perceive touch interactions and so on and so forth. So I'm happy to take any questions.
Thank you very much, Stefan, for this very nice presentation and of this very nice work. I see so many kind of applications that I would have a hard time to define just one. Yeah. Is there any question in the audience? Yeah, Maud is typing. Again, do not hesitate to take the mic if you'd like. And
question?
Yeah, Reza.
Hey, thank you very much. I'm Reza from Vrije University of Brussels.
Mm-hmm.
Thank you for your presentation. I actually have a question about your sensors. I want to know, can you detect different modes of your finger, for example, differentiate between twisting, bending, and other kinds of motions with the signals of your sensor?
Yes, so that's an interesting question. So the paradigm I follow here is that the capacitive sensor allows really to find the location of the contact, so where the force is being applied, and then the cavity structure inside the model will help us in quantifying the force. So to find the correct direction of force, so in this case we are assuming that a normal pressure or a normal force, we would need a special arrangement of the cavities, I think. So not any device can be easily equipped. For instance, detecting torsion around the axis of force on the pad would be difficult, because the capacitive sensing is not necessarily suited for that. So another type of structure, if you imagine you have something that is really a device that is really twistable, for which I am able to find the interaction points and the deformation, yeah, I think that's possible to have twisting motions or sharing motions. It's possible that we are actually already doing some tests for sharing motion. But yeah, I think, yeah, there's some interesting ideas to follow there. We can, for instance, if you follow I don't know if you're familiar with the gel site principle, where you have some markers where you track optically.
Yeah.
Then you can find a vector field of torsion motion, and I think it's also compatible with the modeling approaches and so forth.
Yeah, thank you. Thank you for your information.
Yeah, you're welcome.
Thank you, Reza. I saw the question of Maud, who just asked about how you are actually handling the noise, especially regarding the capacitive sensing that you are using, and the accuracy of the location.
So in this case, this is the evaluation regarding this question for Mrs. Marshall. Here we see the ground truth of the distribution of the contact points, and then how they are estimated by the soft pad. And we see that the accuracy is about 1.5, 1.7 millimeters, which represents about a 3% error regarding the total size of the array. However, I think it's possible to improve in general, and we also found that it was kind of independent of the force. So that's what I mentioned, that as you push on it, you are stretching, deforming the electrodes, but at least to the degree which we tested, we maintain the accuracy and it's robust towards this deformation.
Thank you very much. I see Maurice typing as well. Thanking you. Okay, perfect. Thank you for being part of this first session about soft robotics. There will be a second one this afternoon, so do not hesitate to stay tuned and see what's happening. There will be also other very cool presentations about electromagnetic fields and so on using soft robots. You'll see cool stuff.